but somewhat cleared up in my own head is that it is this earthward convection that's driving the ring current growth, and also push the inner edge of plasma sheet closer to Earth, which intensifies the ring current. I don't suppose I need to use too many magnetogram data to show the DST, which is the monitoring the storm activities, and AL index is the one that monitoring the substorm activity. What you see here is you have those substorm activity way before storm kicked in. And thinking that the storm is driven by substorm, that's a ridiculous idea. Because you can have substorm without storms. And you rarely have storm without substorms. Almost exactly like the situation of substorm and BBF. And this statement is somewhat of a copied Typhon statement that he told me. He said, yeah, Joe, you know, we've seen a lot of BBF without substorm. And we almost always see BBF during substorm. Well, there you have it. And so the important thing to prove now is that BBF does not produce substorm. Thereby what? Thereby substorm does not drive storm. Get it? Something like that. Okay? We just make it oversimplified so everybody could understand. You have substorm going on, nothing, no storm yet, but then later on there's a storm. Okay. This is to prove or to support my claim. It is the day-side reconnection that drives the storm. So we use SIMH is similar to DST. You see the SIMH goes up with the day-side reconnection electric field. It's just one of the expression that myself and Lu Li derived in early days. Nothing profound. All we did is to take Sonorov's day-side reconnection model and then make it geo-effective or put in whatever the angular dependence and so on, and come up with this expression. Oh, well, I didn't show the expression, but it's well, I mean, it's like something like the EKL is equal to Vx Byz times sine square theta over 2, and theta is the angle, they call it clock angle of the interplanetary magnetic field. But what I wanted to show here is not that expression. I mean, that expression is trivial. Actually, I didn't use it until Pat Newell told me. He said, Joe, I tested all kinds of expression, and yours came near the top, only second to mine, he said. I said, that's very good. So, anyway, you see some deviation, and this clock is being, I said there's too big a gap here and there, so I asked my co-worker to fill in more data. Anyway, it is nice because it increases with increasing EKL. But it's not a straight line linear correlation. And there are reasons why it shouldn't be. There are several reasons, and listed here are the observation that show dipolarization, inject particle earthward, and enhanced ring current. And then there are other observation magnetogram show that dipolarization actually disrupt cross-tail current and cause decay or reduce of the ring current, the DST. So these two maybe depending on where that polarization is, sometimes edge in and sometimes take away. But this one is definitely contributing to ring current, and that has to do with the aurora acceleration potential, right? So we know substorm contribution to ring current is not as straightforward as you might think. So that brings me to this part 3 about talking what causes the substorm. It's driven again by the earthward, global earthward convection, which is powered by the solar wind magnetopulse dynamo. But the story is much more complicated than the title indicates, because it took me a long time, actually. I started out studying aurora in '72. The first thing Shin told me to do, I told Shin I couldn't understand all those negative Bay and all those fancy terminologies. He said, don't worry about it. So I never worried about it. DP2 and all that stuff. He said to read rocket measurement of aurora particles. So I did. I spent a whole year reading those papers, and still couldn't understand how those arc is produced, because I start out with a uniform ionosphere conductance. That's the killer. So much later, maybe only 3 years ago or 4 years ago, then I come across this Dave Hardy's particle precipitation. Dave Hardy is the first one that showed that ionospheric conductance is produced by the combination of diffuse aurora and discrete aurora. And in fact, the main contributor to oval conductance, I call it now, is coming from not discrete aurora. Discrete aurora is very narrow layer and located, and this oval conductance is a global non-uniformity. In fact, it is that oval conductance non-uniformity and anisotropy leads to not only the generation of discrete arc, and also the substorm dipolarization onset. Okay, now I know this come at a time when most of you already start to doze off, but this is a very important slide. This got the quantitative understanding of how dipolarization starts. actually, I venture to state that 1 and 2 are the necessary and sufficient conditions for substorm dipolarization onset. I stick my neck out quite a bit. It may be proven to be wrong, but it cannot be completely wrong, okay? Just like it cannot be completely right either. That's how science progresses, right? But this got the essence, I believe. Has got hold of the essence of substorm onset mechanism. And these are not just talking or hand waving or whatever else. It is a simple derivation based on the overall conductance being non-uniform and anisotropic. And I don't want to go into detail now because it's all written out in detail in that paper. So the important thing is that you need to have this earthward convection to have enough speed, maybe above 10 and below 20, between 10 and 20. That'll give you a decent overall conductance with sufficient energy in the plasma sheet to produce what you need to make the Cowling electrojet go over 5 times the Peterson current. Peterson current is the original convection electric field. Okay? So I don't need to increase the westward electric field, earthward convection to increase 5 times without even increasing any of that electric field. I get Cowling electrojet to increase by 5 times. But of course, it didn't come from nothing, right? It comes from the induced southward electric field, which is well known even in Chattanooga days. When I first came here, Chattanooga was hot. And it shows, I remember, it shows westward electric field start to rotate. Equatorward, bang, substorm onset starts. This CMOS data might be a little complicated for people who are not used to looking at these plots. But what the important message I wanted to bring out from these are that it shows dipolarization, either BZ increase or magnetic tail angle increases. So there are 2 dipolarization events here. And how it relates to the ground observed onset arc, brightening of onset arc. And that was tricky. I don't have time to go into detail. At the same time, you see the AL increases, negative AL increases as IMF goes southward. So this is all consistent with everything I said. In fact, this is the slide. I worked with two PhD students. I said, well, you start out with IMF, and you look at AL, and bang, bang, bang. No selection of data, okay? There are plenty of data. And came to this 2 substorm dipolarization event. And there's all kinds of people telling me, hey, this is not 2 events, that's just the same event, this and that. I said, don't confuse me. And lo and behold, the first event is now known as the so-called pseudo breakup. The second event is a genuine substorm dipolarization. So you can call the first event pseudo dipolarization or pseudo substorm. Now the interpretation was after looking at all kinds of aurora, ground-based CMOS aurora images, and this person at Berkeley, Harold Frey. I went to talk to him. I said, I'm no expert on this aurora images and so on. So he looked at it and then he told me, you can put it in the bank. The first event is super breakup. The second one is a genuine, full-fledged dipolarization. And once that's settled, and he showed this, which is, he called it image total. That's what allows you to determine the timing of onset arc, brightening of onset arc. Very important. The pseudo breakup was no problem. It went up straight. But the genuine dipolarization or substorm event has a little bit of a hesitation in the aurora brightening. Although the magnetic field dipolarization was very straight up. So I spent quite a bit of time here in order to make sure I don't make a mistake here, because the time delay between these two, onset arc and dipolarization onset, is of critical importance in determining whether your substorm onset is initiated from the ionosphere or initiated from the tail. So I spent almost a year, definitely more than half a year, working on this, and then got hold of a Russian modeler, magnetic field modeler. She had done, well, I should have her name, but her name is on the paper. Anyway, with all the fuss, I mean detail, turns out brightening of the onset arc precedes dipolarization onset by 80 seconds. That 80 seconds is then determined to be the travel time of our phase wave from the ionosphere to the dipolarization onset region. Now that's a very important statement. If that went wrong, I'll be in the hot soup. So after that, I know I need to show what the model looks like. I call it CECL, Cowling Electrojet Current Loop. See, this is the first time I use current loop, and that cross at the dynamo is the second time I made use of it. Because if it's not in the loop, you have no current. It'll stop. Okay, so, all right, before I indulge on it, this is the loop CECL is initiated, started from the ionosphere when the wave front propagates, say, wherever the wave front is where your field align current has been enhanced. And that is where you can have your aurora acceleration to produce the aurora in the ionosphere. So as it comes up somewhere, it'll cause the brightening of the onset arc, which has to be very close to the ionosphere, near ionosphere. But when it left the ionosphere and then start to propagate by the offend wave front, when it impinges on the near-Earth plasma sheet, that's where you get your dipolarization, disruption of cross-tail current. So this is before dipolarization, because the offend wave hasn't reached this cross-tail current around 10 RE, and this is after dipolarization. Now, the nice thing about this is that you follow this, it produced the observed substorm current wedge for you. You don't need to mess around. Naturally, just like UAF is naturally inspiring, right? Okay, so anyway, I think this is quite exciting in my career to be able to say so. And then after that, I know I still have a problem. The problem is, what's the driver of earthwork plasma convection, earthwork global scale convection? Is it tail reconnection, or is it something else? And I guess I must be lucky to stumble on to this solar wind magnetopulse dynamo, and I look at it, and I said, lo and behold, it's right there. You don't need to look any further. It's there. If you realize the closure of that current, dynamo current in the loop through the plasma sheet, Lorentz force of that cross-tail current drive the earthward flow. Now, when I saw that, I quickly sent an email to my friend Vasilievich. He was good. He didn't have any problem, he said. He made some correction because I said my cross-tail current drive the earthward flow. He said, no. It's the Lorentz force. So that's good, right? That's what friends are for. Anyway, now this comes to my conclusion. Conclusion, I think it's pretty simple, right? And I hope it's simple enough for you to remember what the story is. Thank you.